Good evening, students, and welcome back to another gently unfolding journey here with the Pillow Professor. I'm so glad you've joined me tonight. Tonight, we'll be drifting slowly through the cosmos, exploring something truly magnificent, the life cycle of stars, these glowing giants above us, so tiny to the eye yet unimaginably vast, have their own stories born from clouds of gas and dust, living for millions or even billions of years, and ending in dramatic, beautiful, and sometimes mysterious ways. We'll follow them from their humble beginnings in cold, dark regions of space, through their brilliant main sequence years, all the way to their fading moments as white dwarfs, dense neutron stars, or enigmatic black holes. It's a story of transformation, of time, and of the universe itself told in starlight. So if you haven't already, I invite you to like and subscribe so you can continue learning with me, night after night, and I'd love to know where in the world are you listening from tonight. Leave a little comment below and let me know whether it's a cozy corner in your room, a rainy night on the coast, or a quiet stretch of countryside. You're part of our stargazing classroom now. Now let's close our eyes to the world around us and open our minds to the stars above. Our journey begins in the quiet nursery of the universe, where stars are born. Imagine, if you will, a place where light has not yet begun, a place deep in the darkness of space, quiet and still, where time seems to stretch and silence fills every corner. Here, tucked away in the vast arms of galaxies, lie the stellar nurseries, immense clouds of gas and dust called nebulae. They are not empty, nor are they static. Though they may seem like frozen clouds to our eyes, they are alive with motion, gently stirred by gravity, magnetism, and the faint whispers of passing stars. The material within them is mostly hydrogen, the simplest and most abundant element in the universe, along with traces of helium, carbon, and cosmic dust, the leftovers of stars long since gone. For millions of years, these vast clouds float aimlessly, until something disturbs the balance. Sometimes it's a nearby supernova, the explosive death of a massive star, sending ripples through space. Other times, gravity simply becomes too strong to resist. Slowly, softly, regions within the nebula begin to collapse. As gravity takes hold, pockets of gas and dust are drawn inward. They spin ever so gently at first, and then faster and faster. Pressure builds. The particles begin to rub together, colliding and heating up. What once was cold and quiet is now warming, glowing, a cocoon of potential. This is the beginning of something new, something radiant, something that will one day shine. Within these clumps, a core begins to form, dense, hot, and hidden within swirling clouds. This is what we call a protostar, the earliest stage of a star's life. It is not yet luminous like the stars you see in the night sky, but inside something extraordinary is happening. The core grows hotter as more material falls inward. At first, the heat radiates away, and the protostar remains cloaked, but gravity continues its slow, inevitable work. Layers of gas pile on, pressure builds even further. The temperature climbs higher, rising from thousands to tens of thousands, and eventually to millions of degrees. It is here, deep in the heart of this forming star, where a powerful transformation will soon begin. As the protostar matures, powerful jets of energy shoot from its poles, carving channels through the surrounding cloud. These jets help regulate how fast the star gains mass, like a baby breathing its first gasps, exhaling into the cosmos. Yet it's not quite a star, not yet. The secret to becoming one, to truly ignite, lies in a process so vital that it powers every twinkle we've ever seen. This process is nuclear fusion. But before we dive into that next phase, take a moment to appreciate this. Everything you are, everything you've ever seen, owes its existence to clouds like these. Stars are not born in fire and chaos, but in slow collapse, deep silence, and patient gravity. In the darkness of these cradles, The universe writes its first glowing sentence in the story of a star, and soon that sentence will burn bright. So, as the core continues to heat and the pressure becomes too much to contain, something astonishing is about to happen. The protostar will cross a threshold and the universe will witness the birth of a true star. Let's drift now, gently into that moment of ignition. Somewhere deep in the belly of a collapsing cloud, the heat has been building for what feels like an eternity. The protostar, still shrouded in its envelope of dust and gas, is slowly preparing for a transformation that will change everything. With every passing moment, gravity squeezes tighter, the core becomes denser, hotter, and more energetic. Temperatures reach beyond 10 million degrees, and finally, quietly, invisibly, something extraordinary occurs. The hydrogen atoms in the protostar's core, once floating freely, now move so fast and collide with such force that they begin to fuse. This process, nuclear fusion, is the engine of starlight. It is nature's alchemy, where hydrogen is transformed into helium, and in the process, a tremendous amount of energy is released. This energy pushes outward, creating a delicate balance with the inward pull of gravity. The result is something beautiful, a stable, shining star. For the first time, the protostar begins to shine, not just from heat, but from the very fire within its heart. This moment is its true birth. Now visible beyond its dusty cocoon, the newborn star takes its place among the cosmos. Its light travels across space, reaching other stars, drifting past planets, and eventually, maybe even to the eyes of curious beings like us. But becoming a main sequence star is not guaranteed for every protostar. Some never gather enough mass to ignite fusion. These become what astronomers call brown dwarfs. Objects not quite planets, not quite stars. They glow faintly in infrared light, quietly existing in the spaces between definitions. Yet for those that do gather enough mass, those that ignite, a long and steady life awaits. How long that life will be depends on how massive the star is at birth. The larger the star, the more quickly it burns through its fuel. Paradoxically, the most massive stars live the shortest lives, some only a few million years. Meanwhile, smaller stars like red dwarfs can burn steadily for tens or even hundreds of billions of years, far longer than the universe has even existed. But no matter the size, all stars spend the bulk of their existence in what is known as the main sequence, a period of stability, light, and quiet energy. Before we reach that long glowing phase, it's worth reflecting on this incredible threshold. The ignition of fusion is more than just a technical milestone. It's a profound change, a declaration perhaps that something has truly begun. What was once a cold, dark speck in a nebula has become a brilliant beacon radiating warmth and light into the darkness. And so the protostar, now transformed, finds its rhythm. It shines, it burns, it lives. So let's continue, floating gently now into the heart of a main sequence star. Picture it like this. Gravity is always trying to pull everything inward, trying to crush the star into a tiny point. But the fusion at the core, that incredible transformation of hydrogen into helium, generates an outward pressure that pushes back. These two forces, one compressing and the other expanding, meet in perfect harmony, and when they do, a star achieves equilibrium. From a distance, the star appears peaceful, like a tiny twinkle in the night sky. But deep inside, it's a churning cauldron of energy. Every second, countless hydrogen atoms are fusing into helium. This process releases energy in the form of light and heat, which takes thousands of years to reach the surface, and then streams outward into space, traveling for eons before it may touch a planet, warm a moon, or illuminate a distant sky. Stars in this phase can vary dramatically in appearance depending on their size and temperature. The smaller stars, known as red dwarfs, are cool, dim, and incredibly efficient. They burn their fuel slowly, like a candle flickering in the dark. These stars can last for up to 100 billion years or more. Their lives are so long, in fact, that not a single red dwarf has ever died in the history of the universe. They are all still burning gently since their formation. Then there are the more familiar stars, like our own Sun. These are yellow dwarfs, with medium mass and temperature. Our Sun has been in its main sequence for about 4.5 billion years, and it has several billion years still to go. Its glow is steady and nurturing, bathing Earth in warmth and making life as we know it possible. And finally, there are the giants, the massive hot blue stars that burn with intense brightness. These stars shine fiercely but live fast and die young. A blue giant might only last a few million years before exhausting its fuel and moving into its dramatic final stages. It's as if they live their entire lives in a brilliant sprint, while the red dwarfs take a slow, quiet stroll through cosmic time. But regardless of size, the main sequence is a time of relative peace in a star's life. It is a time of light, of constancy, of subtle evolution. The star remains stable, growing ever so slightly brighter and hotter over time. Its outer layers ripple gently with convection, while the core remains a constant forge of transformation. During this phase, stars are not only shaping themselves, they're shaping the worlds around them. They create planetary systems, melt frozen comets, and provide the energy that powers ecosystems. Every tree, every breath, every ocean tide on Earth is tied to the radiance of our main sequence star. And while this stage is long, it is not forever. Slowly, the hydrogen in the star's core begins to run out. The balance that once held firm begins to shift. Fusion slows, the core contracts, the outer layers swell. A quiet change is coming, and with it, the star must begin the next chapter of its life, one of transformation and expansion. So now, let us follow the star as it grows older and begins to change. As we gaze into the night sky, it's easy to think that all stars are more or less the same, just tiny white dots scattered across a velvet backdrop. But in truth, each star carries its own unique signature, quietly etched into its color, temperature, and brightness. Stars, like people, come in a wide variety of types, and their appearances reveal much about who they are, how long they'll live, and what fate awaits them. The science of classifying stars is known as stellar classification, and it helps astronomers organize the many personalities of the universe into something a little easier to understand. Next come the B and A type stars, also very hot, and still quite luminous. They shine white or blue, and while they live longer than the O types, they still burn through their fuel at a rapid pace. As we move further down the scale, the stars grow cooler and redder. F-type stars shine with a soft yellow-white glow, and G-type stars, like our own Sun, burn with a familiar golden hue. These stars are often referred to as dwarfs, but don't let the name fool you. Our Sun, while considered average in size and brightness, is still over 100 times the diameter of Earth and more than 300,000 times its mass. And finally, we reach the M-type stars, the red dwarfs. These are the most numerous stars in the universe. They are small, faint, and cool, glowing with a soft red light. Though they may be overlooked by the naked eye, they are quietly abundant, like grains of sand in the cosmic ocean. Their longevity is unmatched, living for hundreds of billions of years, long after all the larger stars have gone dark. The color of a star doesn't just tell us its temperature, it tells us its story, its age, its future, its inner workings. It tells us how much mass it holds, how long it will shine, and what sort of ending it will one day meet. If you could float among the stars and look closely, you'd see this rich tapestry of hues and sizes, some tiny and cool, others large and hot, each one a fiery testament to the forces of physics, gravity, and time. And yet, no matter the type or color, all stars are born from the same basic ingredients. What makes them different is simply how much material they gather in those early moments of formation. A slight difference in mass at birth can decide whether a star becomes a long-lived red dwarf or a short-lived supergiant. It is a reminder that in the universe, as in life, small differences at the beginning can lead to vastly different paths. Now that we've met the many faces of stars, from blue giants to red dwarfs, it's time to look a little closer to home. Let's gently turn our attention to a star that is very special to us, one we know intimately, even if we sometimes forget how remarkable it is. Let's drift toward the heart of our solar system, to the Sun. In the quiet darkness of space, one star shines brighter in our lives than any other. It is the constant presence in our sky, the bringer of warmth, the keeper of time, and the very reason life exists on Earth. It is, of course, the Sun. Though we often take it for granted, rising each morning, setting each evening, the Sun is far more than a celestial clock. It is a living, breathing sphere of nuclear fire, humming with energy and dancing with magnetic storms. It is our local star, a G-type main sequence star, and it has been shining steadily for over 4.5 billion years. The Sun is vast, so large that over 1 million Earths could fit inside its glowing frame. At its core, temperatures soar to over 15 million degrees Celsius. This is where the magic happens. Deep within that fiery heart, hydrogen is being fused into helium, releasing a steady stream of energy that slowly makes its way outward. This energy takes an astonishing journey. It begins in the core, moving outward through a dense zone called the radiative layer. Here, photons, tiny packets of light, are absorbed and re-emitted countless times, bouncing around for hundreds of thousands of years before they reach the next layer, the convective zone. In this outer region, heat rises in giant loops, like bubbling porridge, carrying energy to the Sun's surface. From there, light finally escapes into space, taking just 8 minutes to travel 93 million miles to reach us. That sunlight warms our skin, grows our plants, and powers our winds and oceans. It fills our days with brightness, and without it, Earth would be a frozen world, silent and still. But the Sun is not always peaceful. Its surface is a boiling sea of plasma, constantly in motion. Sunspots, cooler, darker patches, appear and disappear in rhythmic cycles. Solar flares and coronal mass ejections send powerful bursts of energy into space, sometimes reaching Earth and painting our skies with shimmering auroras. Despite these outbursts, the Sun is remarkably stable, a quiet star by cosmic standards. It spins slowly, completing one rotation every 25 days at the equator. It holds more than 99% of the mass in our solar system, anchoring the planets, moons, comets, and asteroids in graceful orbits. And while the Sun seems eternal, it, too, is on a journey. It is about halfway through its life on the main sequence. For now, it is content, steadily converting hydrogen into helium, balancing gravity with fusion, shining with dependable light. But in about 5 billion years, things will begin to change. The hydrogen in its core will start to run low, the delicate balance will shift, the Sun will swell into a red giant, its outer layers expanding beyond the orbit of Mercury, maybe even Venus. That's a story we'll reach soon enough. For now, though, it's comforting to know that our Sun is steady, a glowing guardian in the sky, a quiet flame that connects us to the stars. As we leave our local star and float once more into the depths of space, we begin to wonder what happens when a star like the Sun runs out of fuel. Let us now follow the path of aging stars and discover what comes next in their grand celestial lives. For billions of years, a star like the Sun lives in quiet balance, gravity pulling inward, fusion pushing outward. But eventually, even stars run low on fuel. Slowly, silently, the hydrogen at the very core begins to dwindle. It doesn't happen all at once. The outer layers continue to shine as though nothing is wrong. But deep inside, in the star's heart, something has changed. The hydrogen that once filled the core is mostly gone, replaced by helium, the byproduct of fusion. This renewed fusion adds an unexpected twist. The extra energy causes the outer layers of the star to expand. The star swells, growing larger and larger. Its surface cools slightly as it stretches outward, giving the star a reddish hue, and just like that, the main sequence phase comes to an end. The star has become a red giant. To stand beside one would be overwhelming. A red giant can be hundreds of times larger than its main sequence self. If the Sun were to become one today, it would grow so vast that Mercury and Venus would be engulfed, and Earth would feel its heat in ways we cannot imagine. The surface, now cooler than before, would glow a soft, deep red, beautiful but ominous. But this second balance is short-lived. Helium burns faster than hydrogen, and soon it too will begin to run out. For stars like our Sun, the journey ends here. They do not have enough mass to ignite further fusion. The core cannot collapse into heavier fusions like neon or iron. Instead, the outer layers of the star are gently pushed away by the last pulses of energy, drifting into space like a shimmering veil. The star, once vast and glowing, sheds its outer skin, revealing its heart. What remains is small, hot, dense, and glowing with a pale white light. This is the white dwarf, the final stage for many stars like our Sun. But before we explore that quiet ending, we'll take a closer look at the red giant stage itself. What does it look like? What becomes of those drifting outer layers? And how does a dying star paint the cosmos with color? Inside, the once simple process of hydrogen fusion has become more complex. Helium now fuses in the core, while hydrogen continues to burn in a shell around it. These overlapping layers of fusion create a kind of instability, like a fire that flickers brighter just before it fades. The red giant begins to pulse, slowly at first, then more dramatically. Each pulse pushes material outward, and over time the outer layers of the star are gently cast into space. This isn't a sudden explosion, but rather a graceful shedding, like petals falling from a giant fiery flower. What's left behind is something hauntingly beautiful, a planetary nebula. Despite the name, these glowing shells of gas have nothing to do with planets. They were simply named so by early astronomers who, peering through primitive telescopes, thought the rounded shapes resembled distant planets. But they are far more spectacular. These luminous clouds can stretch for light years across. They drift slowly into the galaxy, their materials spreading and mixing with the interstellar medium, the great sea of gas and dust between the stars. And within that material lie the building blocks of new stars, new planets, and perhaps one day, new life. At the center of this glowing cloud lies the remnant, the white dwarf, small, dim, and incredibly dense. It is what remains of the star's once mighty core. Though it no longer undergoes fusion, it glows faintly from the residual heat of its earlier life. Roughly the size of Earth, yet with the mass of the Sun, the white dwarf is one of the densest forms of matter in the universe, second only to neutron stars and black holes. It will not explode. It will not collapse further. It will simply fade. Over billions, even trillions of years, the white dwarf will cool, dim, and eventually become a black dwarf, a cold, dark husk that no longer emits light. But the universe is still too young for any white dwarfs to have reached that stage. For now, they drift quietly, ancient embers glowing in the vastness of space. But not all stars go so quietly. Some stars are born far larger, with much greater mass, and their destinies are far more dramatic. Not all stars drift gently into the night. Some are born massive, burning with fierce intensity and living lives of spectacular brilliance. These are the titans of the stellar world, the supergiants, and their journey through the cosmos is a story of power, speed, and ultimately breathtaking transformation. Whereas a star like our Sun will live for over 10 billion years, a supergiant may burn through its fuel in just a few million. These stars are so massive that the pressure in their cores ignites fusion at astonishing rates. They race through their fuel, unable to slow down, their immense gravity and extreme temperatures pushing them forward at a breakneck pace. Like their smaller cousins, Supergiants begin by fusing hydrogen into helium in their cores, but their tremendous mass allows them to go much further. When the hydrogen runs low, they don't stop at helium. One by one, they ignite new fusion reactions, building heavier and heavier elements in layers, much like the rings of an onion. Helium becomes carbon, then carbon fuses into neon, neon into oxygen, oxygen into silicon, and finally, silicon into iron. Each of these stages grows shorter as the star nears its end. The fusion of silicon into iron can occur in just a single day, and yet this final act brings with it an invisible line that cannot be crossed. Iron is the end of the road. Unlike the lighter elements, fusing iron does not release energy. It absorbs it, which means the star can no longer produce the outward pressure needed to counteract the force of gravity. The core becomes unstable, and within moments the balance collapses. In an instant, the iron core caves in on itself. The outer layers, still burning with unimaginable energy, fall inward at tremendous speed. The result is one of the most powerful events in the universe, a supernova, but we're not there just yet. Before the explosion, the star expands one final time. It becomes a red supergiant, swollen to such size that it may encompass entire orbits of planets. If placed in our solar system, some red supergiants would extend beyond the orbit of Jupiter. Their outer layers glow softly, but the core is a maelstrom of fusion and pressure, pushing ever closer to collapse. And when that collapse comes, it is sudden and violent. The inner core shrinks in milliseconds, reaching densities so extreme that protons and electrons merge into neutrons. The outer layers strike this solid wall of matter and rebound outward in a shockwave of unimaginable force. But before we feel the ripple of that explosion, let's pause here and take a breath. The life of a massive star is both beautiful and tragic. It is a reminder that even in the universe, the brightest lights often live the shortest lives. Yet, even in their endings, these stars do not vanish quietly. Their deaths are fireworks that light up galaxies, and their remnants, whether neutron stars or black holes, become mysteries that challenge our understanding of space and time. Next, let us witness the final act, as a supergiant tears itself apart and transforms the fabric of the cosmos in a burst of light. When a massive star reaches the end of its life, it doesn't simply fade away, it erupts. The result is a shockwave, a brilliant burst of energy that rips through the star and blasts its outer layers into space. This is the moment of the supernova. Light radiates outward with astonishing intensity. In distant galaxies, these explosions can be seen with the naked eye from Earth, even if the star itself had never been visible before. But it's not just light that spreads outward. Matter is flung into space at thousands of kilometers per second. The debris from the explosion becomes enriched with heavy elements: gold, silver, uranium, and more. These are materials that could not be made during normal fusion processes. They are created only in the final seconds of a star's life, when temperatures and pressures reach their extreme peak. In this way, the death of a star gives birth to something new. Our planet, the Earth beneath our feet, is built from elements forged in ancient supernovae. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were formed inside stars, and many were scattered by explosions like this. The gold in a wedding ring, the copper in a wire, the iodine in our medicine. These are all the echoes of dying stars. Supernovae do more than create elements. Their shock waves ripple through surrounding space, compressing gas clouds and often triggering the birth of new stars. In this way, one death may lead to another birth, continuing the great cycle of stellar life. There are different types of supernovae. The kind we've just explored is known as a core collapse supernova, and it occurs when a massive star runs out of fuel. But there are also thermonuclear supernovae, which occur in binary systems when a white dwarf steals too much material from a neighboring star. When it becomes unstable, it ignites in a runaway fusion reaction and explodes, leaving no remnant behind. but in the core collapse version, something does remain. At the heart of the supernova, hidden within the expanding cloud of debris, lies the dense core now compressed into an object so extreme it challenges our very understanding of physics. Sometimes it becomes a neutron star. Other times something even stranger emerges. A black hole. We'll soon arrive at that fork in the road. But for now, let's drift in the glowing aftermath. Picture the supernova remnant, a sprawling, colourful cloud of gas and dust, glowing with energy, expanding slowly into the void. Over time, this remnant cools and fades. It may linger for thousands of years, lighting up the space around it like a fading memory. In its center, a new object spins, tiny, dense, and pulsing with invisible force. Let us now move closer to that remnant and discover what lies at the heart of a star's final explosion. In the silent center of a supernova's wake, after the fire has faded and the glowing debris drifts outward into space, something extraordinary may remain: a neutron star. It is, in many ways, a contradiction, tiny yet unimaginably massive, quiet yet born in chaos, invisible to the eye, yet among the most powerful objects in the cosmos. A neutron star is the collapsed core of a massive star. After the supernova, if the remaining mass is not quite large enough to form a black hole, gravity compacts the core into a single sphere, only about 20 kilometers across, roughly the size of a city. And yet, this small object may weigh more than twice as much as our Sun. 1 teaspoon of its material would weigh more than a mountain. At this scale, normal matter no longer exists. Atoms are crushed, their electrons and protons merging to form neutrons, densely packed together like marbles in a box with no space to move. What remains is a ball of pure nuclear matter, so dense that light itself bends around it. But there's something else. As the core collapses, it spins faster and faster like an ice skater pulling in their arms. A star that once turned lazily in days may now rotate several times per second. Some neutron stars spin even faster, completing hundreds of rotations every second. These are known as millisecond pulsars. Many neutron stars also have incredibly strong magnetic fields, trillions of times stronger than Earth's. As they spin, beams of radiation shoot from their magnetic poles. If one of those beams happens to sweep past Earth, we see it as a pulse of light, like a cosmic lighthouse flashing at regular intervals. And so, these spinning neutron stars are called pulsars. Discovered in the 1960s, pulsars were initially thought to be signals from intelligent life. Their pulses were so precise, some more accurate than atomic clocks, that they seemed mechanical, intentional, but they were natural, the universe's own ticking metronomes, marking the seconds of stars that had died long ago. Neutron stars are not immortal. Over time, their spins slow, their pulses fade, and their magnetic fields weaken. Some may acquire a companion, another star, and steal matter from it, flaring back to life in brilliant outbursts of energy. Others remain solitary, drifting through the galaxy in quiet isolation. And yet, there's one more step beyond. If a star is massive enough, truly massive, not even neutron degeneracy pressure can stop the collapse. Gravity wins, utterly and completely, and something darker is born. Let us now take a slow, thoughtful step toward that most mysterious of endings, into the shadowy depths of a black hole. They are black holes. When a star, many times more massive than our Sun, reaches the end of its life, its iron core collapses under its own weight. If the mass remaining is great enough, not even the resistance of neutrons, which holds up a neutron star, can stop the implosion. Gravity pulls inward without limit. No force in the universe can oppose it. The result is a singularity, a point of infinite density, where all the matter of the collapsed star is compressed into a region with no volume, yet immense mass. Around this singularity is a boundary called the event horizon. This is the point of no return. Once something crosses this threshold, be it light, matter, or time itself, it cannot escape. Time slows, light bends, space stretches. If you were to approach a black hole, an outside observer would see you freeze at the edge, fading to red, never quite falling in. But from your perspective, you would fall through in seconds, though what happens beyond that point remains unknown. Some black holes spin, warping nearby space into a whirling maelstrom. Others drift silently, remnants of long-dead stars hidden in darkness. And at the center of galaxies, including our own, lie supermassive black holes, containing the mass of millions, or even billions, of suns. How these enormous black holes form remains one of astronomy's greatest mysteries. Perhaps they grew from ancient stars, feeding slowly over time, or perhaps they formed early in the universe, seeds planted in the chaos after the Big Bang. Black holes can also collide and merge, sending ripples through the fabric of space-time, waves that can now be detected here on Earth. These gravitational waves carry the echo of cosmic events that occurred millions or even billions of years ago, letting us hear the final sighs of ancient stars. Despite their darkness, black holes reveal themselves through their surroundings. They pull in matter that forms hot, glowing disks as it spirals inward. Some eject jets of material that stretch for thousands of light years, marking their presence in dramatic fashion. And yet, for all their power, black holes are quiet, invisible, elusive. They are the final destination for some of the most massive stars, the ultimate expression of gravity, and a reminder that even in a universe filled with light, shadows play their part. We may never fully understand what lies beyond the event horizon, but in contemplating black holes we are drawn to the edge of knowledge, to the boundaries of time, space, and understanding. And from there, we look outward once again. Though stars may die, their story doesn't end in silence. The universe, ever patient, gathers their remains and begins again. Every star that has lived and died has given something back. The gentle breath of a red giant, the fading shimmer of a planetary nebula, the thunderous release of a supernova, all of these moments scatter material into the cosmos. And within those winds, those clouds, those ashes, are the seeds of future stars. This is stellar recycling, a cosmic loop in which death feeds life. The gas and dust expelled by dying stars drift slowly through the galaxy, becoming part of the interstellar medium. Over time, these scattered atoms, carbon, nitrogen, iron, oxygen, and more, gather into great clouds once again. These are the molecular clouds, the same cold, dark nurseries we visited at the beginning of our journey. Only now, they are richer. They are not made of just hydrogen and helium, but of elements forged in ancient hearts, the bones and breath of long-forgotten stars. When a nearby event, such as a supernova shockwave or a passing gravitational wave, stirs the cloud, parts of it collapse. Gravity, always the quiet sculptor, begins to shape the cloud into clumps, and within those clumps, the story starts anew. Protostars form, fusion ignites, and young stars are born, surrounded by disks of dust that may one day become planets. In this way, the universe is not static. It is constantly evolving, reshaping, and building upon itself. The atoms that were once part of one star may now reside in another, or in the soil of a planet, the wing of a bird, the breath of a child. Our own solar system was born in this way. The sun, the earth, the moon, all emerged from the remnants of stars that lived and died long before our planet ever formed. Even our bodies carry this legacy. In the grand scale of the cosmos, we are not separate from the stars. We are their continuation. Astronomers have a saying, "We are stardust," and while poetic, it is also scientifically true. We are built from the ashes of stars, shaped by their light, held in orbit by their gravity, nourished by their warmth. And so the cycle continues, from cloud to star, from star to dust, from dust to planet, and from planet, sometimes to life. The universe is a vast, interconnected system. Every star that dies creates the conditions for something new, And through this cosmic recycling, galaxies remain alive, glowing, breathing, changing. As we float through this great cycle, it's humbling to think that nothing is ever truly lost. Stars are born, stars die, and from their remnants the next generation emerges, more complex, more enriched, more capable of creation. Let us now step back and take in the full picture, to understand the life cycle of stars not just as a sequence, but as a story, one that echoes through time and space. Light is the most ancient messenger in the universe. Long before Earth was formed, before the planets spun, before oceans stirred, before even the first atoms came together to form the molecules of life, there was light, and most of it came from stars. Every time you look up at the night sky, you are gazing across time. Each point of light you see is not as it is now, but as it once was, a glow that may have traveled for hundreds, thousands, even millions of years to reach your eyes. Some of that light began its journey long before humans walked the earth, long before Earth itself had solid ground. Stars are time machines. Their light holds the fingerprints of the past, subtle patterns called spectra that tell us what they're made of, how old they are, how far they've traveled, and what direction they're moving. With this light, astronomers read the history of the universe, like archaeologists brushing dust from ancient stone. Even when a star dies, in a quiet sigh or a final explosion, its light continues to travel. Some of the stars that grace our sky may no longer exist, but their radiance lives on, still moving forward, still speaking. And in that light, there's warmth. Not just physical heat, though stars provide that too, but a deeper warmth, the warmth of connection, a reminder that we are not separate from the stars. We are shaped by them, touched by them, even composed of their scattered remnants. The sunlight that filters through your window each morning, the faint twinkle of Venus in the evening sky, the soft glow of starlight on a still night, all of it is a bridge, a thread from the vastness of the cosmos to the quiet of your room. The next time you see starlight, whether it's a blazing constellation or a single faint point against the dark, take a moment to think of its journey. That glow may have crossed unimaginable distances and drifted silently through the void, just to find you. Even now, as you listen, your own body emits light, not visible to your eyes, but a faint infrared glow. You too are part of this radiant web. Just as stars shine, so do we. Perhaps not with nuclear fire, but with thought, with curiosity, with life. And maybe, just maybe, that's the universe's way of knowing itself. Through light, we see the stars. Through stardust, the stars became us. Let us now continue, floating gently toward the future of starlight, not just in the lives of stars, but in the stories they inspire. The stars have always been our oldest companions, ancient lights scattered across the night sky, constant and distant. But for most of human history, they were unreachable, untouchable, silent. Now slowly that silence is beginning to break. With telescopes that stretch the limits of vision and spacecraft that journey beyond the pull of Earth, we are beginning to understand stars not just as pinpricks of light, but as physical places, immense, complex, and real. The James Webb Space Telescope, floating far beyond our atmosphere, peers into the past by capturing light from the earliest galaxies. It shows us stars as they were when the universe was young, still forming, still gathering. We are witnessing starlight that began over 13 billion years ago, from stars that no longer burn, in galaxies that have long since changed shape. With instruments like these, astronomers can watch stars in every stage of life. They can observe stellar nurseries in exquisite detail, where dusty clouds swirl and collapse. They can study dying red giants and the elegant shells of planetary nebulae. They can trace the trails of supernova remnants and the invisible pull of black holes. And there is more to come. One day, we may visit the worlds around distant stars. Already, astronomers have discovered thousands of exoplanets, planets that orbit suns beyond our own. Some are large and gaseous, others are rocky and warm. A few lie in the narrow range of distance where liquid water could exist. These are the places where perhaps life might arise, nourished by a star just like ours. And maybe somewhere out there, life already has. It's humbling to realize that the stars we study may themselves be gazing back, that in another corner of the galaxy, other beings might be looking at our sun and wondering if someone is looking at them too. The more we learn about stars, the more we learn about ourselves. Their fates mirror our own: birth, growth, change, and transformation. Their light illuminates not just the universe, but the questions we carry inside us. Why are we here? What are we made of? Where are we going? And the stars, burning quietly, dying spectacularly, and recycling endlessly, offer part of the answer. They show us that the universe is not still, it is alive, it moves, it breathes, it creates. We are part of this great unfolding, made of stardust, shaped by gravity, warmed by light, and connected by time. And maybe, in that reaching, we become something more. If you could drift above the galaxy, beyond the spiral arms, above the glowing dust lanes, you would see a quiet choreography unfolding. Stars being born, stars living, stars dying, a cycle playing out across hundreds of billions of years, woven into the fabric of space itself. Stars are not just points of light, they are timekeepers, storytellers, the living record of the universe's long and winding history. Every star you see in the night sky is a message from the past. Because of the speed of light, the cosmic speed limit, we see stars not as they are now, but as they were when their light began its journey toward us. Some of the stars twinkling above you tonight may no longer even exist. Their light has simply taken hundreds, thousands, or even millions of years to reach your eyes. And yet, here they are, reaching across time to whisper their stories. Through their colors and temperatures, we can read their youth or their age. Through their motions, we can glimpse the gravitational tides of galaxies. In the earliest moments after the Big Bang, there were no stars, just hydrogen, helium, and a quiet, glowing fog. But then, in time, the first stars ignited, colossal, short-lived giants that lived fast and died violently. They seeded the cosmos with heavier elements, allowing new generations of stars to form, and slowly, the first galaxies emerged. Since then, generation after generation of stars has lived and died, each wave refining the composition of space, each supernova reshaping its corner of the galaxy. And now, billions of years later, we live in a universe rich with starlight, with planets, moons, oceans, and perhaps life scattered across its breadth. Even black holes, those mysterious endings to massive stars, play a role. They anchor galaxies, bend space, and sometimes, in their silent embrace, shape the path of stars and gas on a galactic scale. From a single star in a nebula to vast galactic clusters containing trillions of suns, the life cycle of stars is a thread that connects everything. It is the backbone of cosmic evolution, a quiet hum beneath the roar of the expanding universe. And within that vastness, you and I are small, but not insignificant, because we are part of that same cycle, made from stardust, living on a world that was once ash and gas, looking up at the stars and wondering. The life of a star reminds us that change is natural, that beauty can come from both creation and destruction, that endings are also beginnings, and that nothing, not even the darkest corner of the universe, is untouched by light. As we prepare to bring this journey to a close, let us remember that each night sky is more than a view, it is a story in motion, a living mural of births and deaths, of gravity and fusion, of mystery and meaning. Now, in our final moments together, let's gather what we've seen and gently say goodnight to the stars. And so, dear students, we come to the end of our journey. We began in the shadows of a quiet nebula, in the cool cradles where stars are born. We watched as gravity worked its slow magic, forming the first flickers of light. We followed that light as it grew stronger, steadier, transforming a mere whisper of gas into a radiant star. We drifted through the long years of stellar life, through the patient burning of hydrogen, the slow balancing act between pressure and pull, the glowing warmth of our own sun. We watched as stars aged, expanding into giants, shedding their layers, painting the sky with nebula, or collapsing with force into the dense hearts of neutron stars and the haunting silence of black holes. We listened to their pulses, we studied their colors, we watched them give their final gifts, scattering the elements that would one day become planets, oceans, and life. And we saw that in their endings. There was never silence, only transition, a return to the beginning. Stars do not truly die. They become something else. Their energy continues. Their dust forms new clouds. Their gravity shapes new orbits. Their stories live on. Even now, as you lie here gently drifting, the stars are moving, living, changing. Somewhere in a distant galaxy, a new star has just been born. Somewhere else, an old one has just flickered its last light. And through it all, the universe remains in motion, calm, vast, and endlessly beautiful. As your eyes grow heavier and your thoughts soften, remember that you are part of this great cosmic rhythm. A quiet note in the symphony of starlight, a moment in the endless dance between darkness and glow. So rest easy now, students. Let the universe watch over you, and let the stars, forever ancient and forever young, sing you softly to sleep. Good night.